We all live in a yellow submarine, yellow submarine, yellow submarine. We all live in a yellow submarine, yellow submarine, yellow submarine.
Okay, here's a classic physics word problem. If you've ever watched an old World War II submarine movie, you'll recognize this. When they fire the torpedo, somebody has a stopwatch. Why? It's very, very simple, sort of. First, you got a submarine, and second, we have some sort of target. Now this word problem states that we have a torpedo fired with a speed of 20 meters per second, hitting a target 2,000 meters away. The total sound, this is the sound, the time it takes for the torpedo to go to the target and the sound to come back to the torpedo, the total time of that event is 101.4 seconds, and that's the key to this problem. Oftentimes in physics it helps to draw pictures, so this is my nice artwork. Submarine fires a torpedo. What we know about this is that the speed of this track is 20 meters per second. The torpedo is traveling 20 meters per second. The distance is 2,000 meters. The sound coming back from the torpedo also traveled 2,000 meters. So this is going to be a key. This is what's going to help us. And that is the unknown speed. So we'll call this V sub s for V sound. So we've essentially got two problems here. The first problem is the torpedo. We can figure out the math of that. The second problem is the sound coming back from the target, the explosion, and we can figure out the math of that. Okay, so now that we've got both problems, let's make a little bit of room. One thing that we know is we're trying to find Vs. So in order to find Vs, which is the speed of sound, we need the distance traveled divided by the time it takes to travel. Well, that's a clue right there. We do not know what the time it takes for the sound to travel back from the target to the submarine. So if we knew the time, then we've got something to work with. What we do know is the total time. So the total time is very simply the sum of both of these. So this is the time of the torpedo, let's use a capital T, no reason, plus the time that it takes for sound to come back. So the time for sound to come back means that's really what we need. So we have the distance, 2,000 meters. If we have the time it takes to come back, then we can figure out the speed of sound, which makes it sound easy. So we have this, we're looking for TS. We know T total. All we need is to find this time of the torpedo, and that will give us everything we need. So from this problem, we have speed, and this problem being the torpedo itself. We have the speed of the torpedo and the distance the torpedo travels. So what we're going to do is we're going to figure out this part up here is totally the torpedo. So the time it takes the torpedo to travel, and you can work out the transposing later, is the distance of, and the distance is the same for both, divided by the speed of the torpedo. So I'm going to put V over T. So this T is the same T that we were talking about down here, the speed of, the time of the torpedo. So I can do a little substitution, and I need to clean this screen up, don't I? So let's make a little bit of room here. We'll keep this visual up here nice and neat. Okay, remember the key is the time. We know the total time, we can find the torpedo time so that we can find the time of sound, because that's that one variable that we really, really want. So this is the time that it takes for the sound to come back is the total time. I probably should have used sigma or something instead of writing it out, minus the time of the torpedo. Maybe I should have used A's, B's, C's, 1's, 2's, something like that. So we're on the right track, but we still don't know the time of the torpedo, so we're going to use a little substitution. Okay, the time that it took the torpedo from just before was the distance traveled divided by the speed of the torpedo itself. T equals D divided by V. So I substitute all of this for that time of the torpedo. So follow with me. The time for sound is equal to the total time, 101.4 seconds, minus the time of the torpedo, which we've now had to get all fancy and spread it out. Okay, so far so good. This tells us the time. Why did we want the time? Every once in a while you got to stop and think. What am I solving for again? We're solving for the speed of sound in water. So the speed of sound is equal to the distance traveled, which is the same in both cases, divided by the time it takes for the sound to travel this distance. So now I think you're starting to see a little bit of substitution. We're going to take, and I'll clean it up, we're going to take the distance as normal, which is 2,000 meters from our problem, and then for the sound, the time of sound, we're going to do all this. So let me clean it up again. The speed of sound is equal to the distance traveled divided by the time it takes to travel. So the distance is the easy one, and we're going to substitute from the last problem. We're going to take the total time subtracted by the time it takes for the torpedo to travel this distance. So we're going to do distance divided by the speed of the torpedo, because that gives us the time of the torpedo itself. Okay, now's a good time to pause and think about it for a minute, because I've combined quite a bit of stuff here. Now we could try to simplify the problem, but honestly, if you look at it, we have the distance, we have the total time, there's the distance again, we have the speed of the torpedo. Every single one of these variables is listed in the word problem. We know that that equals the speed of sound. So all I really have to do is plug it in. It looks annoying, painful. I would rather do that than try to simplify this, although, yeah. So what we want to do is we'll just rewrite what we have up there, but we're going to pay attention to the units. Always do that before we plug in numbers. Up at the top, the unit for distance is meters. Down at the bottom, the unit for time is seconds. And then inside here, it gets real fun. We have meters divided by meters per second. And that's not as bad as it looks. Okay, yes it is. Okay, just remember, the more you do these, the easier it gets, and you're not going to have to do all these steps. The important question is, why in the world do we pay attention to this? Well, we want to make sure we have the answer right. We've got to get the concept. Let's go ahead and look at everything in here first, and then we'll just apply that. So deep inside here, we have the top times the reciprocal of the bottom. So inside of these, we can just cross it out and write the unit seconds. So seconds minus seconds, it doesn't go away, it stays the same, is just plain seconds. So really all of this fancy stuff just comes down to meters per second. And remind yourself again why that matters. Well, all of those units were so that you could solve for the speed of sound. Meters per second is the correct unit for speed of sound, so it's not as bad as it looks. We're just double checking we got it right as long as we plug in the numbers. So now that we've convinced ourselves the problem is set up right by looking at the units, let's plug it in. The distance is equal to 2,000 meters. The total time is 101.4 seconds. And then inside the parentheses, we have 2,000 meters again. Now, could you do all these individually? Sure. Divided by 20 meters per second. Now, I've already done the units, so all I got to do is pay attention to the numbers. A little easier to work out than it looks. Cancel out some zeros. We have 200 over 2 is 100. So the time becomes a heck of a lot simpler. So let's make a little bit of room. What we end up with is the same 2,000 meters at the top. You know what? I'm going to leave off the meters because we've already done the units. Make sure I don't accidentally put a decimal. So 101.4 seconds minus 100 seconds. Yes, I just said I was going to ignore the units for a little bit. This is getting sloppy. The neater you can write, the better you'll do. Because obviously you got to go back and read your own handwriting. So all this really boils down to, again, we've already done the units, is 2,000 divided by 1.4. What am I doing? I'm trying to find the speed of sound. Now, how many times have I gone back and said, what am I doing again? Don't worry, that's part of physics. We're trying to find the speed of sound. We know that it is meters up top, this other stuff we did before, seconds on the bottom. So the speed of sound is 2,000 meters divided by 1.4 seconds. So I don't have a calculator on hand, but I know that's going to be less than 2,000. So the speed of sound, if I remember right, is like 1,400 or something like that, meters per second. And there you go. That's how we solve the problem. Okay, fine. I got a calculator and worked it all out. And I guess my memory's not so bad. The speed of sound, and this is in water, is about 1,428, okay, we'll round, 1,429 meters per second. This is in water. And once again, think about your answer. Go back to the problem to think about it. We have a torpedo that traveled 20 meters per second, which is pretty quick, and it took, it was 2,000 meters. So yeah, that's about 100 seconds to get there. It's a total of 101.4 seconds. So if you remember the World War II movies, the captain yells, "Fire!" Okay, no sound effects. And the torpedo's going off. There's a guy with a stopwatch around its neck counting it down. He's already done all these calculations. Torpedo comes down, there's an explosion, and in 1.4 seconds the sound comes back. So to travel 2,000 meters in 1.4 seconds is a really, really high speed. Is 1,429 meters per second a really high speed? Absolutely. Just a historical note, this is exactly what they did on the submarine in these old movies. And you've got the added pressure of you got to hurry up because the enemy's firing on you. You better do it right. If you get it wrong, well, now they know you're there. If you hear an explosion too soon, in this case, earlier than 101.4 seconds, you know you hit a different target. If time goes by and it's over 101.4 seconds, you know you missed the target and now you're in trouble. They know you're there. It's time to hide. So, little history note. Sorry. It looks more complicated than it is, but when you work through and try this stuff out, you'll realize that with practice it gets easier and easier and easier. Just like all sorts of things that you have to practice. So I would rate this problem as moderately hard, not because of the math, not because of the physics, but because you had to combine two problems, you had to figure out what they had in common. You really had to think, you got to figure things out, and that's what physics is about.
Boston has